Hello, everyone. My name is Yashong. I'm very glad to be here to present our work, Multimodal Conversational Fashion Recommendation with Positive and Negative Natural Language Feedback. This is a joint work with Craig MacDonald and Iad Unis from University of Glasgow. Conversational recommendation is a type of conversational information-seeking task that aims to elicit the user's dynamic preferences and recommend items according to their current needs through multi-turn interactions. Multimodal conversational recommendation is specifically concerned with a goal-oriented sequence of multimodal interactions between users and the recommender systems. Here is an example of conversational fashion recommendation. In this use case, the users give natural language feedback that describes the differences between the user's preferences and the system's recommendations in order to obtain items with more preferred features. In the previous research, to learn satisfactory recommender systems with enough training data, user simulators have been used as surrogates for real human users in the optimization and the evaluation processes. In a real-world shopping scenario, users can express their satisfactions positively with I like or negatively with I dislike, according to the quality of the recommended fashion products. Here is an example of both positive and negative natural language feedback in the conversational recommendation task. The recommender system is expected to update visual recommendations with more preferred features based on positive feedback and avoid recommendations with undesired features based on negative feedback. However, there are no datasets for conversational recommendation with both positive and negative natural language feedback. For this reason, the existing research imposed several constraints on the user's natural language expression to simplify the multimodal conversational recommendation task by either only describing their preferred features as positive feedback or rejecting the undesired recommendations without any natural language critics. Therefore, the impact of positive and negative natural language feedback on the effectiveness of multimodal conversation recommendation has not yet been fully explored. In this paper, to make the conversational recommendation task more realistic by supporting both positive and negative natural language feedback, we propose an approach to generate both positive and negative critics about the recommendations with an existing user simulator for relative captioning. In particular, we swapped the positions of the target item and the candidate item. So the relative captioner can describe the features of the candidate image that are not contained in the target image. It's worth noting that we adopt templates as wrappers to handle the user's positive and negative utterances, so as to reduce the errors for natural language understanding and generation. Following previous work, we train and evaluate the two existing multimodal conversational recommendation models, the dynamic manager model and the multimodal interactive transformer model. The feedback texts are encoded with a BERT-based text encoder, while the recommended images are encoded with a ResNet-based image encoder. The GRU component allows the DM model to sequentially aggregate the recommendations and the feedback information to the estimated hidden states, while the transformer-based state tracker enables the MIT model to attend to the entire history of the multimodal interactions. Based on the estimated state of the user's preferences, a list of candidate image items can be recommended for the next interaction term. For fair comparison, we train the tested models with attributed loss objectives by considering the target image as a positive sample and a randomly sampled image as a negative sample. A post filter is used to remove the previously recommended items in the recommendation ranking list. We performed the experiments on a well-known fashion dataset with shoes images. Following common practice, training and evaluation use a user simulator. At each interaction term, the user simulator gives feedback on the candidate images that are the most or the least similar to the target image. Success is measured by getting the target image in less turns and ranking it more highly at given turns. For the first research question, is positive natural language feedback more informative relating to the user's preferences in comparison to the negative natural language feedback? The figures of the experimental results show the effectiveness of the tested models with positive or negative single sentence feedback for top 3 recommendation in terms of NDCG at 10 and success rate, while varying the number of interaction turns on the shoes dataset. The solid lines show the model's performances with positive natural language feedback, while the dashed lines show the performances with negative natural language feedback. Comparing the results in the figures, we observed that both DM and MIT models generally achieve a better overall performance with positive feedback than negative feedback in terms of NDCG at 10 and the success rate. To quantify the improvements, we measure their performances at the 5th and the 10th interaction terms. The table of the results contains 2 parts. The first part reports the effectiveness of the models with either positive or negative feedback. The second part reports the effectiveness of the models with different combinations of positive or negative feedback. We observed that both DM and MIT with positive feedback achieve a significantly better overall performance in terms of both NDCG at 10 and the success rate at the 5th and the 10th interaction terms than those with negative feedback respectively. Therefore, in answer to the first research question, positive feedback is more informative relating to the user's preferences than negative feedback. For the second research question, can the combined positive and negative natural language feedback enhance the ability of existing GRU and transformer-based models incorporating the user's preferences? Figures illustrate the success rate of DM and MIT with different types of natural language feedback at the various interaction turns respectively. The gray lines show the tested models' performances with a single sentence at each interaction term, while the lines with the other colors show the performances with a pair of sentences. We observed that both DM and MIT with paired positive or paired negative feedback sentences achieve a better overall performance in comparison to the models with a single positive or single negative feedback sentence. Furthermore, the performance of DM and MIT differ with a pair of both positive and negative feedback sentences. Overall, in response to the second research question, we find that The single type of natural language feedback at each turn can be aggregated to leverage the information relating to the user's preferences, while the paired positive and negative feedback make it challenging for DM and MIT to elicit the user's preferences. The third research question is that what's the impact of the natural language encoding on the model's performances? The figures show the effects of the textual encoding mechanisms on both DM and MIT with different types of natural language feedback. The figure on the left demonstrates that both DM and MIT with positive feedback using the one-hot encoding achieve an overall better performance in comparison to those with the bird encoding. The figure on the right shows that the performances of the tested models with both positive and negative feedback using the one-hot encoding are dramatically degraded compared to those with the bird encoding. Overall, in response to the third research question, we find that the bird encoding is important to capture the contextual information with the pre-trained contextual embeddings when there are both positive and negative feedback. While the one-hot encoding can enhance the model's performance by using a predefined fashion vocabulary that is more concentrated on fashion features than bird. To consolidate the results observed in the above sections, we present a use case of DM model with positive and negative feedback. For file comparison, the initial images are the same across the tested models, given the target image from the test set. In particular, DM with positive feedback only needs 2 interaction turns to display the desired item in addition to the initial random recommendation by capturing the key features from the user's positive feedback, such as gold, open-toed, high heels, and the straps. However, DM with negative feedback fails to recommend the user's desired shoes within 5 interaction turns. Although DM with negative feedback can successfully capture the open toe feature from the rejection of the closer toe feature, it's still struggling with the decisions of the colors and the thickness of the platform. In conclusion, we find that positive feedback is more informative relating to the user's preferences than negative feedback. Different combinations of positive and negative feedback can greatly affect the performance of the both tested models. The textual encoding mechanisms can also greatly affect the performance of the both tested models. Furthermore, we plan to investigate an end-to-end model with pre-trained transformers in fashion, such as fashion birds and the clear belt, to better incorporate the user's preferences from positive and negative natural language feedback and the visual recommendations. In addition to visual and textual modalities, an increasing number of live shopping videos with audio signals are available to display and introduce fashion products in a more vivid and detailed way, such as TikTok live shopping. So we also plan to incorporate such a more advanced modality into the multimodal conversational recommendation. Thank you, everyone. If you are interested in our work, you can find more details in our paper. Thanks.